Okay guys, I'm just waiting for my camera to focus here. There it goes. And this is going to be the video on math induction that we did in class. Now in class I started out with the steps of induction, so you would know how IB or what IB expects when you do an induction problem. But you know, it's easy to learn this through examples, so I'm going to go over the examples that we went in class first, and then I'll review the steps. Okay, so the first thing we did was one of the easiest examples. It says prove that 1 plus 2 plus 3 plus ... plus n is equal to n times n plus 1 over 2 for n as an element of the positive integers. Okay, so let me just put a piece of paper over this, make it a little bit better there. Okay, so the first step is you want to show the grader P of n is this statement 1 plus 2 plus 3 plus 4 ... plus n is equal to n times n plus 1 over 2. Okay, move that over a little bit. Sorry, I'm using my document camera, the one that I scan your bubble sheets with, and I've never really made a recording with it before, so here we go again, something new. Okay, so all I'm doing is I'm taking this statement that includes the variable n, and I'm saying this is the statement P of n. Okay, the actual really first step that I want to show is the basis statement. I need to show that this is true for n equals to 1. So I write to the grader, show n equals to 1 is true. And what I see here is that on the left hand side, so essentially what I'm going to show is that the left side equals the right side when n is equal to 1. In the statement, when n is equal to 1, the output or the result is 1. So on the left hand side it's 1. If I plug a 1 in to the right hand side for n, I get 1 times 1 plus 1, which is 2 over 2. And I can cancel that out, and I see that the left hand side equals the right hand side, so I've shown that n equals to 1 is true. Basis statement or basis step. 2, I need to do the inductive assumption. I need to say assume, and I need to write this, that n equals to k is true. And then what I need to do is I need to rewrite this statement, but instead of putting n's here, I'm going to substitute a k in for every n. So 1 plus 2 plus 3 plus 4 plus ... plus k is equal to k times k plus 1 over 2. Okay, I'm assuming that's true. Now this is important because in the next step, the inductive hypothesis, what I need to do is show that this is going to be true for the kth plus 1 term, and I'm going to use this in the next step. So step 3, I need to show that n is equal to k plus 1 is true. Alright, so what I'm going to write now is 1 plus 2 plus 3 plus 4 plus ... plus k plus 1, the next term, is equal to, and now on the right hand side, you know, I'm going to fill in k plus 1 times k plus 1 plus 1 over 2. So all I've done was I've taken all of this, I've added the kth plus 1 term, and on the right hand side, for every k that I saw, I substituted k plus 1. So what you need to realize is that I said a minute ago I'm going to use this assumption in this part or in the next step. What you need to realize is that this part right here is n equals to k. So what you're going to do is you're going to substitute this with the right hand side of that equation, k times k plus 1 over 2. Don't forget to add, use a different color, the kth plus 1 term, okay, is equal to k plus 1 times k plus 2, so I'm just simplifying that, over 2. Okay, and now what I'm going to try and do is make the left hand side look like the right hand side, and one way I can do that is I can rewrite these over a common denominator. So if I multiply this quantity here, and you can write it like that, by 2, then I'm going to have k times k plus 1 plus 2 times k plus 1 all over 2. Still doesn't look like the right hand side, but I can see that if I factor out a k plus 1, I'm left with k plus 2 over 2. And now the left hand side is equal to the right hand side, so I'm done with that. Okay, so I've shown it. I've shown that n equals to k plus 1 is true, because I've shown that the left side equals the right side. The fourth thing is that I have to write a hence statement, because IB likes that. So I say hence P of k is true, implies that P of k plus 1 is true. Okay, so and so number 5, the last step, that's my therefore. Therefore, P of n is true by math induction. Done. Okay, so the steps that I presented in class are here. For every statement, you want to write out P of n equals whatever. Okay, show the statement's true for n equals to 1 by plugging in the 1 and showing that the left side equals the right side. Write out the inductive assumption that n equals to k is true, so you're just rewriting the statement with k substituted in for n. You're going to show the inductive hypothesis, meaning that you're going to show that this statement is true also for n equals to k plus 1. So again, this is all on EDSB. Once you've done that, you're going to write your hence statement, okay, and then you're going to write your therefore statement. So let's look at the next one. The next statement is this. Says the following. Show that 1 plus 4 plus 7 plus da-da-da plus 3n minus 2 is equal to n times 3n minus 1 divided by 2 for n greater than or equal to 1. Okay, so I start off P of n. My statement is 1 plus 4 plus 7 plus dot dot dot. I'm just rewriting it. It's a little tedious. Okay, and I might not want to lose that either, because generally that information is going to go back into your hence or your conclusive statement. Okay, so step 1 is the basis. Show n equals to 1 is true. Okay, and this is good enough to write for IB. They'll accept that. So again, if I look here, when n equals to 1, I get 1 on the left hand side. And when I plug in a 1 on the right hand side, I get 3 times 1 minus 1 over 2. And if I clean that up, that's 2 over 2. So the left hand side is equal to the right hand side. That statement's done. The next one I'm going to write is assume n equals to k is true. Okay, so I'm going to have 1 plus 4 plus 7 plus 3k minus 2 is equal to k times 3k minus 1 over 2. Okay, and then, oops, I'm going to show my inductive hypothesis that n equals to k plus 1 is true. And I'm going to do that by writing out the statement and adding k plus 1 term to it on the left, and then I'm also going to add the k plus 1 on the right. So k plus 1 times 3 times k plus 1 minus 1 over 2. So now at this point I want to show that the left side equals the right side. Again, I'm going to use that assumption from above, and I'm going to replace all of this mess with that. So this is k times 3k minus 1 all over 2. And now I'm going to clean up this little piece here, so don't forget about that. Plus, inside here I'm going to have 3k plus 3 minus 2, so I guess that gives me 3k plus 1. And I'm going to go over here and clean up a little bit here. It's k plus 1. It's going to be 3k plus 3 minus 1 is 3k plus 2. And again, I'm going to try and make the left side look like the right hand side. And I'm going to put this over a common denominator because the left hand side of this thing is all over 2. So this is k times 3k minus 1 plus 2 times 3k plus 1 all over 2. And you just focus on the left hand side. So if I look here, I can't factor out anything like a k plus 1 or whatever. It's not quite as easy as the last one to just factor out a k plus 1 or something and be left with 3k plus 2. So if I want to, what I can do is I can simplify as much as I want. So if I distribute, I'm going to have 3k squared minus k plus 6k plus 2 over 2, which gives me 3k squared plus 5k plus 2 over 2. And I think this is factorable to 3k. If I put the 2 here, that's going to give me a, oops, I'm sorry. I'm really sorry. Yikes. Okay, so sorry, but I combined here. I distributed, combined. And so now if I put a 2 here, I'm going to have a 6, and 1 would give me 7. If I put the 1 here and the 2 here, I'm going to have 3, and 2 is 5. So plus 1 plus 2, and lo and behold, the left hand side looks like the right hand side, and so I've done that. Now, a little bit bigger. Now I need to write my hence statement, LA. So I'm going to say hence P of k is true implies that P of k plus 1 is true. 4k greater than or equal to 1, because remember, back up here it started out with n greater than or equal to 1, so that restriction was there. And number 5, therefore P of n is true. You could write for n greater than or equal to 1 by math induction. And that concludes the proof of that one. The next one that we did was prove that 2 plus 2 squared plus 2 cubed, on and on, is equal to 2 to the n plus 1 minus 2 for all n greater than 1. Okay, so I know that my statement can be written like this. Okay, I'm going to write my basis statement. Okay, show that n equals to 1 is true. Well, when n equals to 1, the left-hand side is 2. And if I plug in a 1 on the right-hand side, we're going to have 2 to the 1 plus 1 minus 2, which is 2 squared minus 2, which is 2. Left-hand side equals right-hand side. I've shown my basis statement. Step 2, we're going to assume n equals to k is true. So we have 2 plus 2 squared plus 2 cubed plus 2 to the k is equal to 2 to the k plus 1 minus 2 for k greater than or equal to 1. So I'm just kind of copying the statement, but instead of an n, writing a k. And now I'm going to write my inductive hypothesis. I'm going to show n equals to k plus 1 is true. So 2 plus 2 squared plus 2 cubed plus 2 to the k plus 2 to the k plus 1 is equal to 2 to the k plus 1 minus 2. And again, this right here is just my assumption, my inductive assumption. So I'm going to replace it with the right hand side. 2 to the k plus 1 minus 2 plus 2 to the k plus 1 is equal to 2 to the k plus 2 minus 2. Now what I can see here is, I can clearly write this as 2 times 2 to the k plus 1, right? 2 to the k plus 1 plus 2 to the k plus 1 is not 4 to the k plus 1. These are bases raised to some power. So, but I can say there's 2 of them, so it's 2 times 2 to the k plus 1 minus 2. And again, my goal is to get the left-hand side to look like the right-hand side. Well, I'm just going to remember that there's a 1 here, and the bases are the same. And if the bases are the same, then that means I can add the exponent. So I can write this as 1 base, 2 to the k plus 1 minus 2, which is 2 to the k plus 2 minus 2. And now, oops, the left-hand side definitely looks like the right-hand side, so I've done that. Step 3, I'm going to write my hence. Hence, P of k is true implies that P of k plus 1 is true for k greater than or equal to 1. Oops, that was number 4. 5, therefore, P of n is true for n greater than or equal to 1 by math induction. Capiche? The next problem says prove that, now we're dealing with the integers here, okay? Prove that 1 times 2 plus 2 times 3 plus 3 times 4 plus blah 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 plus n times n plus 1 is equal to n times n plus 1 times n plus 2 over 3 for n in the positive integers. Okay? So again, I'm going to write my statement, put it over here. I'm going to write my statement. P of n is 1 times 2 plus 2 times 3 plus 3 times 4 plus n times n plus 1, and that's equal to n times n plus 1 times n plus 2 all over 3, where n is an element of the positive integers. So my basis statement is I'm going to show n equals 1 is true. When n equals to 1, I get a 2 on the left. 1 times 1 plus 1 times 1 plus 2 over 3 gives me 1 times 2 times 3, or 6/3, which is 2. So I've shown that the left-hand side equals to the right-hand side. I'm going to assume that n equals to k. So 1 times 2 plus 2 times 3 plus 3 times 4 plus k times k plus 1 is equal to k times k plus 1 times k plus 2 over 3. And for step 3, I'm going to say show n equals to k plus 1 is true. So, rewriting it, tedious, plus the kth plus 1 term, so that's going to be k plus 1 times k plus 1 plus 1 is equal to k plus 1 times k plus 2 times k plus 3 all over 3. And again, this part here I'm going to replace with the right hand side. I'm not going to forget to add this part. And essentially, I'm just going to work on the left-hand side to see if I can get it to look like the right-hand side. So, again, I'm going to put this all over a common denominator because that's what's going on here. So I have k times k plus 1 times k plus 2 plus 3 times k plus 1 times k plus 2 all over 3. And what I notice is I can factor out a k plus 1 and a k plus 2. So if I factor out a k plus 1 and a k plus 2, then what's left for this term is k plus, the only thing left in the second term is 3 over 3. And I've gotten the left-hand side to look identical to the right-hand side. So I've done my job there. 4. Hence, P of k is true implies P of k plus 1 is true. Okay, and you can say, you know, for k an element of the positive integers, I would just follow that. And then 5, therefore P of n is true. N is an element of the positive integers by math induction. Fini. Okay, at that point I handed out a worksheet that may be a little bit weird. It's going to make you think for sure, but I want you to try those for the next time and we'll see how you do. Let me know if you have any questions. Talk to you Thursday. Have a great day off tomorrow. Bye.